All right, in this video, we're going to go through how to implement a vertical PNP transistor in the Sky130 technology in Magic and an Xschem. It does leave a little bit to be desired. There may be some issues with the way the PDK is set up, both in terms of the SPICE models and in terms of the way Magic extracts the devices. So I believe I have a workaround for that, but here we go. So we're going to cd into Documents and PNP2, and we'll fire up Magic. And let us set up the grid. Now, the Sky130 technology only allows, officially anyway, for two very specific PNP geometries. One of them has an emitter area that is 0.68 microns by 0.68 microns, and the other one has an emitter area of 3.4 microns by 3.4 microns. And it turns out that the only layout that is valid, quote unquote, for these devices is the layout that is supplied by Skywater. And so that's been provided to us as a magic cell. And so the way that we're going to implement these things is basically to instance that magic cell. So we'll go up here to cell place instance, and this cell is one which you'll be able to get from the course canvas page. It's called Sky130 FD PR PNP 05E5 WOP68 LOP68.mag. It turns out that the only one of the two devices is actually available right now in the PDK. Apparently the other one is there somewhere, but it's not one that came with it. So we're going to be using the 0.68 one for those of you who need it. So let me zoom to selection. So this is the device. It is basically an N-well, although the N-well is has a special name. It's called N-base, and that allows Magic's extractor to recognize this device as being intended to be a vertical PNP. So that's this area right here. So if we go C, no, N-base, that disappears. And that is surrounded by a guard ring of P substrate diffusion, and these little contacts here are basically P substrate contacts. And this area here, which has got this opposite hatching, is actually a P well, which is just the P substrate. It's not any different than the P substrate. And inside this N-base region, there's a ring of N substrate diffusion, and these are N substrate contacts or N-well contacts. And this area in here, which is right about there, is P diffusion inside of the N-well, inside of the P substrate, and that makes a vertical PNP transistor. And this geometry, including this number of contact cuts, these little contacts are small enough that these are individual contact cuts, is precisely what the manufacturer requires. So they probably sent this device out for fabrication. They characterized it. They tuned their model parameters to match the characteristics of this device that they fabricated, and this is what you can use. So it is possible to draw a device like this with layers that are here, and it will extract just like this device will, but it is definitely an off-label use for the technology, and the models are not, if you like, warranted by the foundry to match those devices. And so what we're going to do is we're going to put down another one of these things so we can instance a second one. So place instance, and we'll grab a second one of these things, and let's expand that. And so you can see that the geometry that's been provided here has the emitter available on metal 1, and the base and the collector are available on local interconnect. Now, the collector is the substrate, so this device can only be used in an emitter follower configuration. And what we're going to do is we're just going to connect the substrate to the base, and then we're going to take the emitter out, and we're going to tie these two devices basically in parallel with each other. So I'm just going to make a rectangle here. Let's say a local interconnect. And I'm going to make another rectangle here of metal 1. And let's put some labels here. So we can go label, and this will be the ground, north, and this is in local interconnect. And let's put a label here. This will be emitter in metal 1. Let's just zoom in to see that we actually have those labels. There's emitter, there's ground, and so let's save this as PNP 2. And so we're going to extract this. So we're going to X to spice, scale off, X to spice, C thresh, infinite, extract all, X to spice. Okay, so let's see what we got. So what we got is two devices, and it extracted it as a subcircuit called Sky130 FDPR PNP 05V0. There's an area parameter. It looks like because the two devices are in parallel, it wrote out the area of both emitters, which is twice times 6.68 times 0.68 microns. And the second device apparently got an area of 0 because the area of the first device was the same as the area of the second device, or included in the area of the first device. So the order of the terminals came out basically emitter, base, collector. That's actually a problem because the actual order of the terminals in ngSpice for a PNP device is collector, base, emitter instead. And to make matters slightly worse, the PNP transistor model in the PDK actually has a fourth terminal, which is the body, or the substrate. These devices actually live in the substrate, so there is no separate substrate terminal, so that's kind of a little screwy. So I have a workaround to deal with that in the schematic for LVS purposes and for simulation purposes. So let's go through that, but this is what we get when we extract from Magic. So now what we're going to do is fire up Xschem. And I have two schematics, PNP toot.sch. So this is a test harness for actually simulating these devices. So I've defined a new symbol, and this symbol is sort of a special PNP transistor symbol, which will be in the zip archive that has the magic cell in it as well. And this device is a subcircuit wrapper for the PNP, the 0.68 by 0.68 PNP device that's in the Sky130 PDK. And it does two things. One is it maps the name of the subcircuit model for the PNP and the PDK, because the model name extracted by magic is different from the device that's in the PDK. The device in the PDK is called, Sky130 FDPR PNP 05E5 underscore W0P68 L0P68, and so this symbol basically is has a name that matches the way the device extracts in magic, and it also swizzles the order of the terminals so that it goes emitter base collector like it extracts from magic, rather than collector base emitter. And then when it calls the subcircuit inside itself, it actually permutes the order so it's collector base emitter, and then it duplicates the collector connection to the substrate connection so that the model in the Sky130 PDK is happy. So just to show you what this looks like, I've got a little test case here where I've just connected these two devices up in parallel like I did in my magic cell. And I'm just sweeping the emitter voltage, and we should get a diode characteristic. We're going to basically just plot the current from through this voltage source, which is basically the negative of the current going into the emitter. And in order to actually, so these are primitive devices, so that when we write out the net list, they don't get expanded into subcircuits. So there's no schematic file that corresponds to these things. And so I've got a SPICE file that includes the subcircuit definition that's appropriate to make these simulate properly. So you have to include this SPICE file along with the TT models in order to get these devices to simulate, but they will simulate, as I will show you here. So if we pull up the net list that's generated, you can see here are our devices, emitter, base, collector, and then here's the name as it matches the devices extracted in magic, or extracted by magic. Here's our include of the library from the TT models block, and here is our include statement of the subcircuit definition for this device that sort of does the swizzling of the model name and of the pins. And there is no sort of extra subcircuit definition here from schematic that corresponds to this symbol. So we're going to simulate this. And there's our IV characteristic, typical sort of exponential that turns on around 0.7 volts. So that looks good. And I've also got a separate schematic here. Which is for LVS purposes. So I basically eliminated the test harness and eliminated the .include file. And so when we write out the net list here, let's see, that's a little too small. We write out the net list here. All we get is these two devices. And so let's save this in our directory, PNP toot, and save that. Yes. And so if we go back out here, we pull up another tab, we can do LVS, PNP toot, Xschem.spice, PNP toot.spice. And so it does complain about property errors because there is no area parameter in these symbols, and so it doesn't have an area parameter to match with the area parameter that's written out by Magic. I didn't feel like it was even really super appropriate to add an area parameter because the area parameter really isn't used by the underlying Sky130 models. This is a fixed size device, and there's a special model that has the area hard-coded because it has a fixed geometry. And so I'm not going to worry too much about these property errors. So if you're using these devices because you're making a band gap, I guess we'll just live with the property errors for the time being. So hopefully that makes some sense and is going to be usable. So if you have questions, let me know. Thanks for watching.